Good morning, Algebra 2. Today we get to look at section 14-2, where we get to choose among linear, quadratic, and exponential models. And the big question we're dealing with is, how do you choose from our set of data? Is it going to be a linear, quadratic, or an exponential model? And what I like to do is do this video in two parts. The first part, I'll do a little bit of what we talked about in section 14-1, do one example, and then in the second video, we'll do some of the problems in the homework assignment, the evens mostly, show you how to do that, and we're going to be using our graphing calculator to do this. All right, now, what I want to do first is, in this first video, is how do you choose which type of what they call a regression do you want to use? Are we going to use linear? Are we going to use quadratic? Or we're going to do exponential? Now, there's two ways of doing this. Now, the way section 14-2 is doing it is they're doing it by putting it as a scatter plot, and then looking at the scatter plot does that scatter plot give a clear indication that it's linear, quadratic, or exponential? Now, another thing I want to do is, before we do that, is if we go back to the last section, and in our last section, on page 703, there's a way that I showed you guys earlier on how to determine if a set of data is exponential, linear, or quadratic. All right, now some of the stuff in section 14-2, it's really not going to stand out very evident, but you can choose as to which type of regression model you want to use. So if you look back at the last section, in part A here, we found that from our set of data or our sequence of numbers, we got a common ratio, not a common ratio, we got a division from one entry to another to be consistent. That will tell you right off the example that this is going to be exponential. Okay, you could probably see that in the graph of it. Exponential is important. One way you can tell it is that your y values really are taking off. They're just flying off the page. It's huge. Okay, that's how you can tell it's exponential. Now, letter B, we did the same thing again by taking the ratios of functions, and we found out they were not consistent. So that tells me that this is not exponential. And what I did over here is took my y values, and we noticed that all our y values have an increase of 6. So that tells me that this is an example of a linear function. And if we were to look at the scatter plot of this, it will look like a linear equation. And what we got to do in this case is we got to treat it as a linear regression, and that means our equation or a model for our equation will be like y equals mx plus b. Okay. Then the third one, letter C, we also see that the ratios here are not the same. They're not consistent. Again, they've got to really be consistent in order for it to be exponential. So again, for this one right here, we noticed that when we did the see what's happening from one entry to another entry, we had to do it a couple of times. Well, if we do it the second time, what's called the second difference, this will be an example of a quadratic function. Again, if you go ahead and treat this in your stats part of your calculator, you're going to see the scatter plot of that, and it will look like a quadratic function. All right, that's one way of doing it. Now, another way we're going to look at today is if we go ahead to section 14-2, and if we look at these 4 diagrams, and I highlighted some part of this thing. This is when you work with data. Here is our data that we have been given. You may not know whether a linear, quadratic, or exponential model will be a good fit. Okay? If the data lie along a curve that rises and falls, falls or falls and then rises, the data may be well fitted for by a quadratic model, but sometimes it may not be as clear. So if we look at these three scatter plots, okay, we can get an idea, and we'll go from, and then from there you can probably figure out what the regression model will be. So if you look at letter A, again, the way this one, if you look at all your points, they all have somewhat of a consistent look. So again, I have here that looks very, very consistent, and its best fit would be, in this case, a linear. All right. Now, the next one, it may look like it's linear, but it's really not, okay? This just takes a little bit of practice. But again, if you look at the way this one is set up, it pretty much looks like this guy is doing something like this. All right. And the best fit for that one would be quadratic. Okay. Now, if we go to letter C and look at this scatter plot, and you get an idea, but pretty much it's going to go like something like this. That's more of an exponential. All right. Now letter D, okay? This one does give, well, if you look at the way it's set up, and I'm going to talk about this one. If you look at this one looks something like this. Now the way that looks, that's an example of a quadratic. But now, if we were to just say, hey, for 1 second, if I was just to eliminate this scatter plot right here, this may give an impression of an exponential. So when we get to doing some examples, this is the one right here where you're going to run across, it may look like a quadratic or it may look like an exponential, but since this point right here, this example right here will be a quadratic. Letter C, that's more of an exponential. Letter B, again, that is not even an exponential, that's more of a quadratic, okay? Because remember now, exponentials, you're going to have, it's going to be a growth or a decay. And letter A is going to be linear. All right, this is what we're going to have to deal with in this section. How do you choose among linear, quadratic, or exponential models for the given set of data? All right, this takes a little bit of practice. Again, there's one problem over within our homework or whatever in our notes. We can say, well, it could be quadratic or it could be exponential. It all has to deal with, you'll see when we get to it, okay? All right, so what I want to do is I want to do one example again. And what I want to do is, if you were to take a moment and go to explain one, again, I've already stated this already. As noted in the Explorer, it is not always immediately clear what kind of model best represents a data set. So with experience, your ability to recognize signs and reasons for choosing one model over another will increase, okay? This takes a little bit of practice, but I don't think you will have any problems. So here's what we're going to do. I'm going to go to page 732, and we're going to do this example right here, and I'm going to do it as best I can to explain it to you guys. I'm going to do it mostly by the calculator, okay? So first things first, here is our set of data. We have years and the number of people in millions, okay? So what we want to do is create some type of a model that gives the most appropriate answer. So again, this is a formula that deals with, an example that deals with population demographics. The data set shows the number of Americans living in multi-generational households. That means more than one generation in the home. That means you, your parents, and possibly your grandparents may be living with you. So what does this model, again, next part is, what does this model predict for the number in 2020 and in 2040? And I'll show you how to do that. So that's why we need to make a model up here so that when it comes time, we plug these values into your equation or your regression model, we can get an idea of how many number of millions will be in the year 2020 or 2040. All right, now what I want to do first is I want to do it based upon what I just showed from section 14-1. Now, right off the bat, I took my sequence of numbers, okay, the number of millions of people, and for purposes, you'll see why in a minute. We're going to be doing this as a stat too. I just made everything start off with 0. So in other words, 1950 starts off with the year 0. 1960 is 10, because you can see here by your XY graph, everything starts off at 0 and everything increases by 10. The first thing I did is, with this problem right here, is I went ahead and found the differences of the first difference. Well, all my first differences are not the same, so I know it's not going to be a linear function. Then over here, I do my second difference. All my differences here are not consistent either, so this may not be quadratic. So this may be, okay, may be an example that may be a exponential. But let's go and look at it first, okay? Like, this is an example that may be either quadratic or exponential. Let's look at it, okay? It's very simple. So take your calculator, turn it on, go to your stat, go to edit, and then L1 is where we're going to put all our values in the X column. So we're starting off at 0. So we go 0, enter, 10, enter, 20, enter, go all the way up to 60, enter. That will take care of us up to 2010. All right, give me a second, plug that in. That will take care of L1. L2 is taking our data that are in millions, just using these numbers. So 32, 27, 26, 28, 35, 42, and 52. All right, so what we're going to do next now is we go ahead and quit out of that. We want to go to y equals. I need to clear out what I did earlier. Make sure plot 1 is highlighted. Okay. We need to do that to take all our data and see what it looks like as a scatter plot. Okay, then we go to graph, go to zoom, zoom stat, and there's our data. Now, based upon this picture, okay, that is a quadratic. Okay. Now, again, there's another telltale sign I want you to see. If you look here at your y's, we go 32, 27, 26, and then it went to 28, 35, 42, and 52. There's somehow or another here, it goes from increasing to decreasing, and then it goes from decreasing to increasing. That's another telltale sign that this is going to be a quadratic. You guys with me? All right, so what we can do now is, we already know that this is a quadratic, so we're going to have to make a quadratic regression of this, okay? Okay, so what you do next is you go to Stat, you go to Calc, and in Calc you find the button that says Quad Reg, which is my calculator's number 5. You hit Enter. You'll get this symbol up here, and all we got to do is go all the way down to Calculate. And in Calculate, it will show us what our model is. So again, I've already did this earlier. So again, our equation would be y equals, in this case, 0.014x squared minus 0.54x plus 31.4. And that is our equation. So what we can do now is, we've already know from the directions, we want to find out how many millions of people will be here in the year 2020. Well, we see 2010 is 60, so that means we have to find out what f of 70 is. That 70 will represent the year 2020. And all you got to do is anywhere in your given, anywhere in your given quadratic now, you let x become 70. All right. Give me 1 second. And then all we got to do is clear what we just did, find out what our number of millions of people will be in the year 2020. Now, this is just a prediction. Remember, now this is a lot of part of statistics. It's just a prediction. Sometimes they go by the data and it creates a trend. Okay. Now, this may be true. It may not be. That's just a trend. So 0.014 times 70 squared minus 0.54 times 70 plus 31.4. Let it do its gyrations, and we get a prediction now of, in this case, 62.2. So in other words, it'll be 62.2 million, which again, it's a little bit higher than 2010. So this is what section 14-2 is all about. Now that's all I'm going to show you right now. I'll give you guys some opportunity to think it through, and then tomorrow I'll do 2 more examples. Like I said, this is not hard. Again, this is all what I did on a calculator that was on the HDNC page 1. We also did it in section 14-1. All right, thank you guys. Tomorrow or the next video, I'll do some examples that have other types of problems. All right, thank you.